Okay, so let's start. Now we will state and prove the ratio test and root test. So the ratio and root tests, which are again for positive series. And the theorem is, the first one is the ratio test. Here is the statement. Suppose an is uh, positive ultimately. So the first terms could be 0 or negative, but after some point on, we want all the terms to be positive. And suppose that this limit exists and or is infinite. So it is, we assume that either the limit exists, so it's a finite number, or it is infinite. Then we have the followings. If this limit is a finite number between 0 and less than 1, then the series and converges. The nice thing about this test is that you don't need any other series to compare with this one. You just work with ANs, okay? The second part is this. If this row is uh, greater than 1, or if it is infinite, then the series diverges. Series diverges. And finally, if row equals 1, then no conclusion. Meaning that the series could be uh, convergent or divergent. Okay, the test just doesn't tell whether it is convergent or divergent. And here is the proof. Okay, so okay, now let's first do this one. So rho is limit an plus 1 over an, and we assume this row is less than 1. Well, if this is the case, so this row is somewhere here. It is strictly less than 1. Okay. Therefore, I can choose a number like this so that the term of the sequence, the terms of the sequence will fall into this gadget for big enough indices. For example, I can choose uh, this radius, let's say epsilon, to be uh, 1 minus rho over 2. Okay, so half of this distance. Okay, and then we know what? All the terms of the sequence will fall into this interval. So this is a positive number. Since by assumption limit of an plus 1 over an is equal to rho, there is some index, right, some integer, so that positive integer, so that n greater than n implies this term minus the limit is less than epsilon, which is 1 minus rho over 2. So this implies what? an plus 1 minus over an minus rho is less than 1 minus rho over 2 and greater than 1, so rho minus 1 over 2. It's negative. Okay. Well, this implies an over an is less than 1 plus rho over 2 and 3 rho minus 1 over 2. The important part is this. So an plus 1 over an, they are all positive numbers, right? For big enough integers. So this is positive, but it is less than 1 plus rho over 2. So it is this number here, okay, this real number. Let's call that real number R. Uh, okay, let's call this real number R, which is a positive number. This means what? So this is true for n greater than n. Okay, well, this implies what? An plus 1 is less than a r times r times a n, and then a n plus 2 is less than n times r n plus 1, right? Because a n plus 1 over a n is less than r. So I have this and I have this, and keep doing this, okay? A n plus n is less than a times, okay, this is of course r squared times a n because this is less than r times a n. So this is less than n plus 2. Sorry. Okay, let me do one more step. A n plus 3 is less than n plus 2, but a n plus 2 is less than r squared times a n. There's another r, so this is r cubed a n. So this way, we see that a n plus n is less than r to the power n times rn. You see, this is fixed for each n larger than n. This thing is less than r to the power n times this fixed number. Okay, so let, for example, k to be a n, which is a positive number. So a n plus n is, and call this number, let's say bn, okay, bn. So this is less than k times r to the power n, and r is 1 plus rho over 2, which is less than 1 because rho is less than 1, right? R is this number. R is this number, the number between 1 and rho. Okay, so, well, you see, uh, R is a positive number less than 1. Therefore, this is the series k times r to the power n, right? With general term k times r to the power n will be the geometric series and it's convergent. So since I have this, since 0 is less than k times r to the power n and k times r to the power n, and from 1 to infinity is convergent, because it is the geometric series, since it is a geometric series. series for uh, with r less than 1. Uh, okay, because we see that bn. What is bn? Bn is just a n plus n, and from 1 to or actually 0 to infinite, but this is the same thing as this one is convergent. This is by the comparison test, right? This thing is less than k times r to the power n. This is convergent. Therefore, this is convergent. But sum of bn's is nothing but the tail of this sequence, and it is convergent. The tail is convergent. Hence, this is convergent. Okay. For the other part, if this limit rho, which was an plus 1 over an, is larger than 1 or infinite, it means what? It means, so this limit value is whatever it is larger than 1. So the terms of the sequence will be larger than 1 after some point on. Okay, they could be close to 1, but they will be larger than 1, or they may go to infinite. Okay, in any case, they will be larger than 1. So that's the conclusion. So an plus 1 over n's will be larger than 1. So there is some, let's say, r here. Okay, you may choose this r to be a number between 1 and rho, and consider this interval like this. Okay, so there is some r between larger than 1, so that uh, an plus 1 over an is larger than r for all n larger than n. So after some point on, all these numbers will be larger than r. But this implies what? As in the above case, this will implies then an plus 1 will be larger than this. An plus 2 will be larger than r times an plus 1, which is r squared an. And this way, we will see that an plus n will be larger than this gadget. Okay? But this time, although this is a geometric series, r is larger than 1. Okay? Larger than 1. So, let bn to be this gadget, then, and this is r to the power times k, k again an. So bn is larger than this term, and r is larger than 1. Therefore, this series is convergent. The geometric series r to the power n is divergent since r is larger than 1, and thus the series bn is divergent by the comparison test. Okay. Well, this implies this bn is divergent, but okay, Bn is this thing, an plus n from 0 to infinity, 0 to infinity, but this is just n from 1 to, no, n to infinity is divergent, divergent. Well, this implies this thing is divergent. So this finishes the proof. Before I pass to some examples, let me remark the following. Uh, the part C of the test. If rho equals 1, then there's no conclusion. Let's see why this is the case. Uh, if rho equals 1, then the test indeed fails, as the examples below show. Okay, first one is this. Consider this series 1 over n squared. So what is rho? Rho is limit an plus 1 over an. Well, that is just limit 1 over n plus 1 squared over 1 over n squared. So this is just limit n squared plus n plus 1 squared. This is 1. And the series, okay. This series is convergent. So rho is 1, and the series is convergent. On the other hand, for the series, or the divergent series, which divergent series? This one, let's say square root of n. This is divergent because divergent by the p-test, right? P is 1 over 2 and less than 1. It is divergent. We still have rho. What is rho? Limit as n goes to infinity an plus 1 over an. This is just limit n plus 1. No, sorry. This will be just square root of n over this. But this is again just 1. So in both cases, rho is 1, but one of the series is convergent, the other one is divergent. Therefore, this test fails if rho is equal to 1. Okay. Now let's see some examples where this series doesn't fail. Okay. Okay, examples. A is this one, 99 to the power n divided by n factorial, 1 to infinity. B is n to the power 5 divided by 2 to the power n, 1 to infinity. C is n factorial divided by n to the power n, n from 1 to infinity. And D is n from 1 to infinity 2n factorial divided by n factorial squared. So let's see each one separately. For the first series, okay, what is rho? Uh, Rho is limit as n goes to infinity. Here an is just 99 to the power n divided by n factorial. So what is this? This is 99 to the power n plus 1 divided by n plus 1 factorial times, this is just n factorial and 99 to the power n. So what is the result? This is limit. I have this guy over here and n to factorial cancels with the first n terms of this product. What is left is just n plus 1 and this limit is 0 and it is less than 1. So limit exists and less than 1. Thus, by the ratio test, the series is convergent. Okay. Okay. What about the second one, which was n to the 5 divided by 2 to the power n? Okay. An is just n to the power 5 divided by 2 to the power n. So what is rho? Rho is limit an plus 1 over an. So this is limit n plus 1 to the power 5, 2 to the power n plus 1, and then 2 to the plus 2 to the power n divided by n to the power 5. So this is just limit 1 over 2 times n plus 1 over n to the power 5. Okay, so this is just limit 1 over 2 times 1 plus 1 over n to the power 5. This 1 over n goes to 0. So this is just 1 over 2 times 1 to the power 5, which is 1 over 2 and less than 1. So it is convergent by the p-test, by the limit, no, by the ratio test. Okay. Third one was n factorial divided by n to the power n. So an is just n factorial divided by n to the power n. So what is rho? Limit an plus 1 over an. So this is limit, okay, n plus 1 factorial divided by n plus 1 to the power n plus 1. And then I have n to the power n and factorial. Well, what is this? This is limit. So this n plus 1 factorial and n factorials simplifies and gives us n plus 1. And then here I have n plus 1 to the power n plus 1. And then I have n to the power n. One of the n plus 1 cancels and we get n to the power n divided by n plus 1 to the power n. So this is just limit, I can write it this way, 1 over n plus 1 over n to the power n. This is limit 1 over 1 plus 1 over n to the power n. As n goes to infinity, of course, well, this is just 1 over e because the limit of this is e. E is like 2 point, right? This is like 2.7 something. So this is less than 1. So again, by the ratio test, the series, which series? N factorial divided by n to the power n is convergent. Alright. Part D is this 2n factorial n factorial squared. Okay, let's see. An is 2n factorial n factorial squared. Limit an plus 1 over an. So rho is this. Limit. When I plug n plus 1, I get 2n plus 2 factorial divided by n plus 1 factorial squared. So it is this divided by an. So this is n factorial squared divided by 2n factorial. Alright. Well, 2n plus 2 factorial divided by this gives us what? 2n plus 1, sorry, times, no, 2n plus 2 times 2n plus 1. And here n plus 1 factorial cancels with this one, and we get n plus 1 here, and same thing for the other two terms. So we have this. And what is this limit? This is 4n squared plus 6n plus 2. 4 and then 2, so 6n. And here we have n squared plus 2n plus 1. This limit is just 4, which is greater than 1. So the series is divergent by the ratio test. Okay. Let's see the root test also. The root test. It is similar, but instead of ratios, we will take roots. Let me write down the statement. Suppose that an are all positive ultimately, and that sigma, which is limit as n goes to infinity, nth root of an, this limit exists or is infinite. Then we have the following statements. If rho, sigma is less than 1, and of course it is positive, then the series uh, converges. So statement is very similar to ratio test. If this is the case, then the series diverges. If rho equals 1, then there is no conclusion. And no conclusion. Okay? The test doesn't tell us anything. I will not prove this. Basically, this same proof, but instead of ratios, you have to deal with ant roots. Okay, let me just do some examples for the root test. Okay, example. Use the root test to check the convergence of the series. Okay, let's see. Solution. So an is just n over n plus 1 to the power n squared. Then, of course, nth root of this is just what? Nth root of this, you take 1 over nth power of this, n squared and 1 over n cancels, and you get n. So this is just n to the power n plus 1 to the power n. So sigma, which is limit of nth root of an, is just limit n over n plus 1 to the power n. This is just limit 1 over, I can write this as follows, 1 over 1 plus 1 over n to the power n, right? This is n plus 1 over n goes up and you get this. But this is just limit 1 plus 1 over n to the power n. So this is just 1 over e, and it's less than 1. So hence, by the root test, the series n over n plus 1 to the power n squared is convergent. Okay, now let's have a break.